Okay, so in this video, what I'm going to do is I'm going to estimate the value of pi. You know pi equals 3.14159. I'm going to estimate what the value of pi is using the mean value theorem. And what I'm going to do is I'm going to apply the mean value theorem to this funny looking function arcsine of x. So this is also known as sine inverse. You've definitely seen this function before. This is what it looks like. So you take a sine function, which is everybody knows, and you do the inverse of it. So that's like flipping the x and the y axes together. You get this funny arcsine function. And the value of pi is baked into this function. And that is because if you do the arcsine of 0.5, if you plug in x equals 0.5, you get pi by 6. So there you go, Desmos has it figured out. The arcsine of 0.5 equals pi by 6. And that's going to be my entry point into figuring this out. So I'm going to estimate pi using the mean value theorem by applying the mean value theorem to the arcsine function. So I'm going to do y equals arcsine of x. This is also known as sine inverse of x. And the entry point that I want to use is that pi over 6 is equal to arcsine of 1/2. If you plug in x equals 1/2, you get pi by 6. That's going to be my entry point into doing this. And the other fact that I'm going to need, and I'll show this fact at the end of the video if you want me to do it from scratch, I think a lot of people know this fact, is that I'm going to use dy dx is equal to 1 over square root of 1 minus x squared. So this is a fact about the arcsine function. Its derivative is the square root of 1 minus x squared. And what I'm going to do, and this is what I said in the last video, the mean value theorem, it is a portal. It is a portal that translates information about the derivative into information about the function. So what I would like to do is I would like to translate this function, which I know very well. I'm going to use the mean value theorem as a portal. I'm going to use the mean value theorem as a portal to convert information about square root of 1 minus x squared into information about pi by 6. So that's what I'm going to do. So here we go. So what I'm going to do, here we go. So pi is equal to 6 times the arcsine of 1/2, because we know arcsine of 1/2 is equal to pi by 6. And now I want to apply the mean value theorem. How am I going to apply the mean value theorem? Well, the mean value theorem converts average rates of change into instantaneous rates of change. So I better make an instantaneous and average rate of change appear over here. So what I'm going to do is I'm going to rewrite this a little bit. 6 times arcsine of 1/2, and this is going to seem a little crazy, but bear with me. Arcsine of 1/2 is equal to arcsine of 1/2 minus arcsine of 0 divided by 1/2 minus 0, all times 1/2. So what did I do over here? The bottom I divided by 1/2 minus 0. Then I multiplied by 1/2. So that doesn't do anything. Multiplying and dividing by 1/2, that's legit. Here I subtracted arcsine of 0. It turns out that arcsine of 0 equals 0. Arcsine of 0 equals 0. You can see that from Desmos because here you go. The graph goes through 0, 0. And that's because the sine of 0 equals 0 as well. So, that's not surprising. So I just manipulated the problem to make it look a certain way. And why did I do that? Because now this whole thing in the middle, this whole thing in the brackets, this is the average rate of change. This is the average rate of change of arcsine on the interval 0 to 1/2. And now that I see that this thing is the average rate of change, I can apply the mean value theorem. So by the mean value theorem, what is it equal to? The mean value theorem says you can replace an average rate of change by an instantaneous rate of change. So this is equal to 6 times dy dx evaluated at x equals c times 1/2. That's what it is. So the thing in brackets, the average rate of change, that got replaced by, this is the instantaneous rate of change. Instantaneous rate of change. It's equal to dy dx at some value x equals c. And the mean value theorem says that c is in the interval 0 to 1/2. But the mean value theorem does not tell you where it is. So this is the mystery of the mean value theorem. We replace this average rate of change by this instantaneous rate of change. We know there is some value c where this works. We don't know what it is. Okay, so what do we have so far? Pi equals 6 times dy dx at x equals c times 1/2. Well, let's simplify that a bit. This is 3 times 6 times 1/2 is 3. dy dx, we have a formula for that. So you take dy dx, you plug in x equals c, you get 3 times 1 over the square root of 1 minus c squared. And this is true for some value of c in the interval 0 to half. So pi equals 3 times 1 divided by the square root of 1 minus c squared. Now the nice thing about this, I don't know the value of c, but I know that c is between 0 and a half. So using this, I have an approximation for pi. There are 2 possible bounds for this thing. This means, therefore, because the function 1 over square root of 1 minus c squared is a strictly increasing function, this means that the smallest possible thing that could happen is c equals 0, and the largest possible thing that could happen is c equals a quarter. So what this means is that pi is definitely in between 3 times 1 over square root of 1 minus 0 squared, and on the other hand, it's definitely less than 1 over square root of 1 minus a half squared, like this. So the mean value theorem tells me pi is equal to something for some value of c. That doesn't tell me what pi is equal to, but because I have a range of values for c, that gives me a range of values for pi. So this one I can do in my head. 3 times 1 divided by square root of 1, that's a 3. So pi is greater than 3, that's pretty good. On the other side, maybe this one's more exciting, 3 times 1 divided by the square root of 1 minus a quarter. Let's simplify this a bit. This is 3 times, I think it's 3 times 1 over the square root of 1 minus a quarter is 3 quarters. So this is 3 times the 2 over square root of 3. 3 times 2 over square root of 3. So pi is definitely between 3 and 3 times 2 over root 3. Let's get my calculator out and see what this is equal to. Calculator time. What did I say? 3 times 2 over square root of 3. What does Google say that's equal to? Yes, I want to leave the site. 3.46410. So that's my estimate for pi, which is approximately pi is less than 3. It is less than or equal to 3.46 dot dot dot. Okay, so kind of a pretty crappy estimate. Another way to write this is pi is approximately 3.23 plus or minus 0.23, something like that. So it's a kind of a crappy estimate for pi, but it is an estimate for pi. And I think this is the first, like, when I was learning math, this was the first rigorous estimate for pi I'd ever seen, was this kind of thing. And in fact, lots and lots of more and more accurate estimates for pi go by this method. So this was the sort of most basic thing you can do. Pi is approximately 3.23, but you can improve it a little bit and get any sort of accuracy you want. So the actual method of using the mean value theorem, it really is like fundamental to how people estimate pi, and this is the most basic thing you can do with it. So, okay, not a great estimate, but it is an estimate nonetheless. Okay, I think I'll stop there. Oh, I promised that I would prove, so you can stop the video now, but if you want, I will prove that for y equals arc sine of x, that dy dx is 1 over square root of 1 minus x squared. So if you know this fact already, you should stop the video. But if you don't know this fact, let me prove it for you quickly. So here's what I'm going to do. I'm going to take y equals arc sine of x. I'm going to invert it. So you invert this, invert it. If you invert it, what does it mean? I'm going to apply the sine function to both sides. So that means that the sine of y is equal to x. And if the sine of y equals x, I can do the derivative of that one. That one I know how to do the derivative of. I'm going to do d dy of both sides. And if you do d dy of both sides, what do you get? One side is dx dy. The other side is the derivative of sine. The derivative of sine is cosine. So the derivative of sine is cosine. So dx dy equals cosine of y. Okay, here's a funny thing. I'm going to write cosine of y using Pythagoras. So this is equal to, cosine is equal to the square root of 1 minus the sine of y squared. That's equal to dx dy. So using cosine squared plus sine squared equals 1. The cosine of y I can write as the square root of 1 minus the sine squared. And that's dx dy. Now I just got to flip it. So this is the square root of 1 minus sine y squared. So therefore, flipping it upside down, dy dx is equal to 1 over the square root of 1 minus cosine of y squared. 1 minus the sine of y squared. Okay, very last step, the sine of y, that's equal to x. So here we go, replace sine of y with x, 1 over square root of 1 minus x squared. That's the proof. dy dx equals square root of 1 over square root of 1 minus x squared. So that's what I used in this thing to calculate this. It really is just coming from the derivative of sine and cosine. Okay, let me stop there.